today, again, talking about the rock cycle, we're looking at how sand, here's two pictures of sand. We just call these baby rocks because these baby rocks came from the mother rock. So big rocks break apart into smaller pieces, continue to roll around and break apart into smaller pieces, and then finally can become soil. So just sand by itself is not a healthy environment for plants to survive. Water runs right through, right? We've got to have some organic matter. So right now we are just talking about the sand. So our key concepts today are that minerals are made of elements. Minerals make up rocks, and rocks are formed in the three environments: igneous, sedimentary, metamorphic. So if you haven't heard these words before, an element, I have a periodic table back here in a minute, and we're going to show you one in just a second. But all of these elements, these are pure. They can't be broken down any smaller. They can't be separated to any smaller. So for hydrogen, all those atoms are the same. Okay, so an element is pure. All the atoms are the same. Elements combine to make minerals. Minerals combine to make rocks. Okay, so it's kind of that building. And again, depending on our environments. So here is your periodic table. Now, for those of you that are my age and older, some of us were forced to at one time memorize this silly chart. Can you believe that? That was such a silly thing. This was never meant to be memorized. It is meant as a tool. So one thing I want to show you is that, well, it took a lot of years for a whole lot of different scientists to get their input into this chart. But basically, I'll give you a quick hint. One side's like think of it as a magnet. One side's a negative or a north, and one side's a south, like a south or a positive. So opposites attract. So when we start talking about how one element combines with another element, it's usually because they're on the opposite sides. And that's why they attract. Okay, they like to share those electrons. So if you think about it, everything in the world can be broken down to this chart. That's pretty crazy because some of these things are naturally occurring, and there is a key that tells you how many are liquids, solids, and gases. But then some of these are also man-made, where we're creating new ones. And that's part of why our space adventures are so important, because again, with the setup in space, you have totally different atmosphere, totally different development of materials. All right, so I'm looking at this periodic table. If I said all the matter on Earth is found in here, are you on this table? Are you as a kid, are you on this table? Your body is made mostly of water. Do you know the scientific compound for water? H2O. So what elements do you think we're talking about? H2O. Can you find hydrogen? It's on the left side. It's number 1. Hydrogen, and then oxygen is going to be on the other side. Oxygen is number 8. So water is H and then 2 oxygens. So it looks like a bear's hat, like a bear's face with 2 little ears. Okay, so that's our water. You need what to breathe? You need oxygen. You know where number 8 is. You breathe out carbon dioxide. Carbon, can you find carbon? It's number 6. Di is just a fancy word for 2. And that's more oxygen, the C2O. All right, so again, everything can be broken down onto that chart. It's pretty cool. Some of the names, if the letters were already taken up, then some of the names may sound odd because they are using Greek or Latin names. And again, you'll learn more about this, but there's also the atomic number, has to do with elements and the atomic mass. So you'll get into that more in junior high and high school, but just know that like one side's negative, one side's positive, opposites attract. So as I go through and explore some of these, you can always look back to this. All right, so one of the first elements I want to introduce you to is copper. Can you find copper on the periodic table? Give you a minute to look. Copper's 29. 29. Okay, so copper is a native mineral. So it is found in the ground, just like this nugget here on the top part, these big nuggets, that comes out of the ground looking like that. After it gets oxidized, it's around the oxygen, gets a little wet. Sometimes it turns a different color, kind of turns a bluish green. As you're around your neighborhoods and all, notice to see if anybody has copper roof or copper guttering or the copper drain chains. The copper is we use as that tubing. You see the metal tubing there? So again, copper is important. We also use it in some of our pots. So again, start looking around your house, see if you've got any of these things around. If you've got a pot that's sitting outside, like your mom or dad puts a plant in it, then it's probably going to be kind of dirty looking and kind of greenish. And that's again because of all the oxygen and the water that's gotten around. All right, so again, copper is an element. We can't break it down anymore. All those atoms are the same. Now, this is a copper mine that is in Arizona. All right, that truck is massive. Look at that big old tractor at the bottom. That's a big tractor. Look how little that truck is. These tires are about 20 feet tall. These trucks are just ginormous. But what's happening is they're digging down into the ground and they're finding the rock that has a lot of this copper in it, but it's called an ore, where they have to get it out of the ground and then they have to separate it. So we have to take the copper out of the heavy rock material. All right. So again, this is looking at another element called mercury. Now, mercury is kind of weird because it's a liquid. You know, we don't have many liquids here on planet Earth with our regular temperature range. And its name goes by HQ. It's also called quicksilver. It's a very heavy liquid, but it is also very toxic, meaning that it's poisonous. So we used to have like mercury and thermometers and all, but now those have all been replaced and they are usually an alcohol base. Okay, but that is mercury. So again, these are pure elements, can't be broken down anymore. Now, when we start combining two elements together, you make something called a compound. So if it's one or more elements, could be 2 or 3, 5 or 6, it's called a compound. So what you see is this compound called halite, and it's recognized by that cubic structure, and it also gives off this light when it's under fluorescent light, gives off a red color, but it actually grows in cubes. I thought only living things grew. Now minerals grow. So when there is room to grow, they do grow as cubes. And again, this is just your common table salt. So when you're done with lessons and all today, later on you can put out a little table salt out on a plate so that you can really look at it good and see how rounded and processed it is. You may have Himalayan salt, you may have rock salt, you might have, there's so many different kinds, and it all depends on how it's been processed. Usually our table salt has been rolled around and processed quite a bit. And of course our salt made of sodium and chlorine. Now sodium by itself, if you take sodium and you put it in water, it explodes like a bomb. Chlorine is a very poisonous gas to us. Okay, we use it sometimes for chlorinating pools. But what's weird is you take these two very toxic elements, you put them together, and they make something very common and very normal. And we use it all the time to flavor our food. So that's kind of odd, isn't it? That it changes those chemicals. I've got a big specimen back here of halite. I don't know if you guys can see it. I'll try to bring it up later. But right at the bay, we do have the company that processes salt, where it's a process of evaporation that salt goes through. Sometimes you'll get hit with those big flubs of the evaporating salt. All right, so this compound, this is talking about how it changes chemically. So we have quartz, which is SiO2, that's the name of our compound, and it is just simply silicon, which is Si, and oxygen. Now what's weird is, how do you get all these different looks? And even if we just study quartz, which is all the SiO, there's lots of different color variations. It's probably one of the most common. But you're used to like that picture in the middle. you are used to seeing like it looks like a pencil, that kind of shape. So that's only though if it has room to grow. So as you're walking around, you may see some quartz like this that's more milky white, that doesn't really have a structure, it's just kind of round. All right, so this is the SiO2, like the pictures you're seeing. And if you look at this rock right here, so this is the outside of the rock. This is what you would dig up, not too spectacular, but when it was cracked open, what you have is this nice geode. Let me see if I can reach it up. So this is kind of like the purple one that's being shown. But again, what happened is there was a little air bubble in between. So there had to be some air in order for the minerals to drip through and create those crystals. So it had to have room to grow. All right. Now, what's really weird though is if you take this SiO2 and you heat it up and you get rid of all of the oxygen, that leaves you pure Si. And this is what pure silicon looks like. And this is what you are named after, Silicon Valley. Okay, it is this element right here. So again, this is doesn't exist naturally because the silicon always wants to bind with the oxygen. So we have to heat it, super high temperatures, get rid of the oxygen. That leaves the pure silicon. And that's what comes out in tubes, and it's sliced thin like wafer slim to make our etchings of our microchips. So again, you're known for the Silicon Valley. But again, these are all looking at how these elements combine, and then sometimes they can be taken apart. All right, so in looking at the rock cycle, I want you to think about, if you haven't studied rocks much, or it's been a while since you've studied them, try to get these pictures in your head. Anytime we talk about igneous rocks, ig is Latin for fire. So think of this fiery hot volcano where it's hot and then those rocks then cool, okay? Because it depends on how the rocks cool if they make crystals or not. So igneous, fiery hot volcano. Water rocks, sedimentary. They've been broken apart and then the water cements them back together. Not like our cement on a sidewalk, but it's like nature cement. So over time and pressure, they're pushed together. So those are water rocks, usually formed in and around water. They usually come off kind of sandy. And then the last one is metamorphic. And those are caused by a lot of pressure and temperature. Sometimes some chemical changes go on. But if you look at where these plates, especially here where you guys live in the next to all of our faults, you have the plate tectonics going on, where you have one plate running up against another one. Here for the Hayward Fault, they're transformed, so they're going this way, okay? So if you take your hands and you rub them together, and you rub them really fast, and you rub them hard, then eventually they build up some heat, right? We're talking about a lot of land there that's moving. That's a lot of heat and pressure. So again, metamorphic rocks can be recooked and rebaked and cooled in so many different ways. Sometimes they're hard to exactly figure out which one is which because they're in the middle. Let's think of it as cooking cookies or a cake. You know, if it's not done cooking it and you bring it out and it's got that middle that's still gooey. So again, sometimes they're kind of in the process. All right, so that's our rock cycle. This is a storybook that is on the website. Teachers, if you want to have your kids do it again and you guys can do your own version of Ricky the Rapping Rock and you guys can dive it up. This has got great content. This was made by a high schooler that went through our program, so she's got all the content in here. But Ricky the Rapping Rock is going to tell you all about the rock cycle.
Yo, my name is Ricky. I'm a rapping rock. I'm here to tell you how I got so hot. I was under great pressure till I reached the top. Folks call me magma, believe it or not. I was flowing down the hill when I felt a change. I began to get cool. Now lava is my name. Outside I was exposed to air and moisture, and I cooled down fast. Magma cooled slow, so water could not pass. Then the storms came, and broke me up a bit. Weathering and erosion created rolling sediment. Here at a new place, I was all alone, till more sediment layered and compacted me to stone. Water moved in my spaces, cemented me together. Yo, my name is Sedimentary because of changes in the weather. Sedimentary can be sorted by the way they were formed. Plastic, chemical, or organic, group them as they are born. Igneous and sedimentary were my former name. Yo, change with heat and pressure as metamorphic to my fame. Yo, my name is Ricky. I am changing all the time. Melt me, squish me, or break me down. Rockin' and rollin' from the top of the hill. I'm Ricky, the rock, rollin' into town. Now let's go back and review the rock cycle. Rock cycle is made out of igneous, sedimentary, and metamorphic rock. Igneous rocks are rocks that were melted and then cooled. Sedimentary are those that are broken and then cemented together. And metamorphic are those that neither broke or melted, changed physically by pressure and temperature. Those are metamorphic rocks. Now let's take a look at Ricky. In this picture here, he's just going through the different cycles just to show you melt me is igneous, squish me is metamorphic, and break me down is sedimentary. This slide shows that igneous and sedimentary were their former names, so that's what they were before, and then with heat and pressure they metamorphosed into a new kind of rock. On this frame here, Ricky has metamorphosed into a rock star, or Elvis Presley. Rock and roll got its name from rocks, and so this is a way in which you can remember the different kinds of rocks, is to remember that Elvis Presley was a metamorphic rock. He liked to glitter and shine. Here we have sedimentary rocks. Notice sedimentary rocks are the only ones that can contain fossils. They are, you can call them wet rocks, but they have to do with a different process on the surface of the earth. When sediments are baby rocks, they get cemented together by things like calcium carbonate, silica dioxide, and it cements them. So this is where these are called sedimentary rocks. It has something to do with water. This picture here shows that as the rocks come down from the hills, it goes into sea level or water level. And what happens is the heavier rocks fall down first. Then as you go outward, they are smaller. And this will lead to different types of sedimentary rocks. Now the storms, when they come, this is where erosion, a mountain, say a volcano, creates a mountain. Rain, water, wind will erode it. And this is how our landscapes are created, is by this added part on our earth of erosion. This slide shows that inside of a volcano, it cools down slower, so the minerals tend to be larger. On the outside, the lava cools down much faster, and it doesn't give the time for the minerals to form, so they're smaller. This one shows that when it comes up, it's called, when it's in the magma chamber, it's called magma. When it comes up, it is called lava. So chemically, they're the same thing. Magma will be the larger crystals, and lava will be the smaller crystals. So this one, it starts when it goes that I'm Ricky, I'm a rapping rock. It's showing you that volcanoes are your mother rock. So you start here, and then all the other rocks evolve as you learn and understand plate tectonics.
Okay. So again, Ricky the Rapping Rock is on our website, that msnucleus.org. If you go to the top left, there's a little logo, and you can go to Storybooks, and under Rock Cycle, you'll find Ricky the Rapping Rock. And with Ricky, it's just the storybook. You have to use those arrows to advance it. So you won't have Dr. Joy singing, but you will have the music behind you. So you can see if you can do your share of Ricky the Rapping Rock. All right, now to continue on with our igneous rock. So this is an example of lava flowing. You see the hot, molten, red, hot lava. Okay, it's magma in the chamber, magma on the inside, lava once it comes outside. But everything that's black around it is that molten rock that has cooled already. And it's cooling very, very fast. So that's where we get very tiny, small crystals. They don't have room to grow big crystals, small crystals. And if you look at this, it's actually forming like locks of hair. This is called Pohoyhoy. And it doesn't matter where you are in the world, we always use the Hawaiian terms for the lava. So either it's Pohoyhoy, like this, where it's real runny, or it's A'a, which is real blocky. Okay, so just know, try to remember again that if it's cools real fast, you don't have minerals. If it cools slow, you do. Let me give you an example. This is a piece of obsidian, and you can see that it is just like black glass. Okay, no crystals, because it cooled very, very fast. That would be the outside of that volcano. Now, cooling very slow. Look at this piece of granite. You can see all the different crystals. You can see black, gray, white, and a little bit of pink. So again, this cooled very slow, had time and room for those crystals to grow. All right. Now I'm going to run a quick video. I want you to pay attention to the power that's involved in this. We're talking about tearing rocks apart. We're talking about exploding the land. Pay close attention to the pieces of molten lava that are going up as red fireballs, but notice how when they cool, they're coming back down as black rocks. Let's see. Big red rocks, and then it comes down. There's one that's coming down as a cooled off black. All right, we call those volcanic bombs. If you look at this, kind of hard to hold with one arm. This is called the volcanic bomb. So this went up fiery hot red, and it cooled slowly as it came back down. It doesn't have the, didn't cool fast enough to make the crystals. But again, you see that in that video. So again, our volcanoes, a lot of power, breaking apart pieces of our earth. Now, another part of the volcanic process are these pyroclastic flows. Super, super hot, just rock that's pulverized, just becomes ash. And if there's snow on the mountain, then that mixes in and it becomes a hot mud flow. But again, look how it continues to billow up, again, because of the heat. And look at how fast it's moving. They can move as fast as 200 miles an hour, and they'll take over everything. And by the way, can you stop lava? Like if you had lava coming and you had a bulldozer, could you push it away and would the bulldozer stop it? No, it would melt the bulldozer. There's no way to stop it. All right, for our metamorphic rocks, again, that area where sometimes the rocks are remelting and sometimes they're just breaking apart. So temperature and pressure play a role in creating these rocks. And it actually changes the way that the molecules line up. So again, sometimes if they remelt again, they become another kind of igneous rock. If they're broken, again, sedimentary. Let me show you an example. Usually your metamorphic rocks are always in layers and are shiny. Okay, this is a piece of schist, shiny schist. It's got lots of mica in it. We use mica in a lot of our makeup, like blush and all, and eye makeup, makes it shimmery. All right, so what piece I just showed you is that schist, where it's squished. It's been under a lot of pressure and heat. So these minerals have been squished so much that they're all laying in the same direction. So it's called foliating, okay, the texture. And if you look at that other piece, the gneiss, the G is silent, so it's not gneiss, it's just gneiss. It has nice lines. So the feldspar and biotite, all those separate into different bands. So it's real distinct colors. Again, that is caused by the increased pressure and temperature. So these are the metamorphic rocks. All right, and our water rocks. Again, think of that running, like a running river, like the ocean. Just think of anything water, where it's moving fast and it's breaking and dissolving those materials. Again, the heavy things drop out, heaviest materials drop out first, then the lighter. To give you an example, this is a piece of conglomerate. See how it's just a bunch of big rocks that have been cemented together. Now, not like concrete cement, not man-made, but this has been cemented by nature. So over a lot of time and pressure, it was pushed together. Okay, so that's a conglomerate. But also remember that the water rocks are the only ones that can hold fossils. So you will see Capitola in just a minute. Notice this fossiliferous mudstone. Do you see the seashells all in it? That's kind of what you see on top of Mission Peak. So again, those are some fossilized clams and all. But again, it's been cemented over time. All right, so with our sedimentary rocks, you've got that large pieces that are stuck together, that's that conglomerate. The smaller sandstone, anything that feels, doesn't really have a lot of this side there. It feels gritty, kind of like sandpaper, okay? But it's not coming off in my hands. Sometimes it's so fine. This is diatomite, where look, it actually comes off. So if you know if the rock is real soft, you know it's a water rock. Okay, so again, this is looking at how big or small these grains are, how it feels. Now remember that our sand is always moving around. Gravity, water, wind, all take its toll on it. And if you go to different places like the beach, rivers, lakes, deltas, deserts, oceans, you will see signs of this motion. So if you look at this one picture where it looks like we're at the beach, we've got a bunch of water coming down. See how it's flowing all different ways? Again, gravity at work. And on the other side, we have ripples. What made those ripples? The UTV that went running down the beach? No, hopefully not. Usually they do a smaller grade. The action of the waves. So the action of those waves, again, rearranges those particles, moves them around, breaks them down, and dissolves them. So this is looking at the bottom of a stream. It's a freshwater stream, but look at how that water's not moving all that fast, but look at the motion that's occurring with the sediment. Is it big things or little things that are moving? Kind of everything all at once, huh? So again, as it's moving, as it's rolling, it's taken thousands of years for a piece to drop off of the Sierras and then make it all the way down to our coast, okay? So again, we're talking about a lot of time to dissolve and break up. And again, I mentioned wind. This is a sandstorm. And as the sandstorm gets closer, it will block out all of the sunlight. You won't be able to even see your face in front of your hand in front of your face, as well as your finish on your car, your paint finish. It's like being sandblasted. if you've ever seen anybody do sandblasting. So again, it can do a lot of damage. Now with this sand, we're going to be talking about its size, the mineral content, sorting, and shape. All right, so if you just look at this picture of sand right in here, after you look at it and you learn some of the key characteristics that I just mentioned, you would be able to identify what is magnetite, all these different, the zircon. Okay, your zircon is going to be your white, the magnetite is going to be dark, but all of these are heavy metals. So you have to be careful where, it's not just people that are polluting. Sometimes our nature also, there are elements that are dangerous. So we just have to be aware of those as well. Again, those elements that can be dangerous. So again, it's just looking at key characteristics. All right, here's your activity.
For our Describing Sands and Particles lab, your teacher will print out a sheet that looks like this. All you need to do is fold it at those dotted lines so that the Describing Sand and Particles is on the front. Inside, you have the shapes and the sorting, and then another grid on the back. So when you are going to go outside, anytime you go to a park or to the beach, simply take this little flyer with you. And all you have to do anytime you get to a park, you could put a little bit of sand in a baggie or a bottle, it doesn't matter, but it doesn't take much. For example, if I just tap the top of this bag like this, I'm just going to very gently let the sands fall out, and then I'm going to try to compare the size of the sand grains to those dots underneath. If you can get a closer look at that. And if you have hand lenses available, you can also use your hand lenses to get a close look at it as well. And now if this is if you're somewhere on vacation and it's somewhere special, if you want to save some sand, all you have to do is simply fold up your piece of paper and it'll drop right back into your bag like that. Now, if you are traveling somewhere different and you want to keep some sand with you, one simple thing you can do is using these little Avery labels. Just peel one off. They're sticky on the back. You can drop it all the way in the sand, and you see how the sticky is going to attach the sand to it. Now, using your glue stick, simply put a little dab of glue on a card, and you can place your sticker with sand right there. Make sure you label and date it with all scientific information, location, so that you have it to save forever.
Okay, does that make sense? So if you're going out to even, anywhere, any of your local neighborhood parks, or even just out to the side where you've got some plants growing, even a small spoon, you can even just pick it up with your own fingers. If it's not your yard, make sure you have permission though, okay? So again, you're just kind of trying to sprinkle on a little bit just to see which sand grain matches up to that dot. Here, I've got another picture I could show you. So you've got two different grids here. The back of that little page has a grid that's kind of darker. So if you have a light colored sand, you could use that grid. But again, you can see it varies. And if you don't have little stickers, that's fine. You can just use any kind of piece of tape. Works good, but it's just a way of saving a very small portion. Remember, if you're going to any national parks and state parks, you are not allowed to collect specimens. Now, a small little piece of tape, I don't think they're going to have an issue with, but you cannot take like bags and bags of sand. So again, we're looking at the size, and this is exactly what a soil scientist would do. It gives us, again, information from pebbles, granules, coarse sand, medium sand, fine sand, silt, and then clay. That's when it gets the squishy clay. This even works if you go to your hardware stores or your landscapers. Again, just start looking around your neighborhood and you'll start to see all these different sizes. All right, so here's your first one to try. We are again looking at this sample beneath, and we're going to try to match these little crystals that we see, the little size of the sand, to this grid. I definitely don't think it's the granule or the very coarse, or even the coarse, right? Thumbs up if you say it's about 250. Okay, thumbs down if you say it's like the 187, if it's the fine sand. And probably somewhere in between. So again, it's not an exact, but it just again gives you a way to help describe, and you're using a number classification to try to describe. So teachers, it would be interesting to ask, do like a survey, ask everybody to grade it and see what they think, and then you would again average it out, and that's then going to be your answer that you would select. So just like politics. So fine, medium, coarse, very coarse, and granular. All right, let's try this one. This is more of kind of a chert sand, like we would find like at Marin or Staten Island. All right, it's definitely not 2000. Definitely not 1500. Definitely not 1000. Not 750. It gets tricky then, huh? So I will leave it to you guys to figure out which you think it is more of a medium or more towards the coarse. Again, I'm looking at the individual pieces. The white, of course, sticks out a lot to me. I think that's probably a quartz. Cherts or feldspars in there. So again, you can find the different minerals. All right. Another thing you're going to look at that is on this little flyer is sorting, how the grains are arranged. If you look at the first one, poorly sorted, that makes sense, right? Little ones, big ones, there's not really, it's not really sorted at all. Poorly sorted, all different sizes. Well sorted, all the same size. Okay, if you look at this example, this is some of the rock from Rodeo Beach. And as you look at, these are actually rocks. They haven't eroded enough to break down into their minerals yet, but it gives you clues on erosion in the cycle, how long they've been rolling around. Poorly sorted is active. So what do you think? Poorly sorted or well sorted? Okay, I'll let you guys come up with your ideas there and pull them together as a class. All right, now shape of particle. Again, you're looking at those individual grains. This is where a hand lens or microscope comes in handy because it looks totally different with the hand lens. See how the one on the right is well-rounded, like a potato. There's not any sharp edges, okay? Angular, lots of sharp edges. So the more it's been rolling around, think of the bottom of that river, it's hitting things, pieces are breaking off. The more it has done that, it becomes more well-rounded, okay? And so this tells a story of how long it's been actively eroding. And again, we're just trying to look at how long they've been in the system. So looking at this one, there's the white pieces look like they're pretty well-rounded. They look like rounded. The sharper brown piece in the middle though, a little more subangular. So again, I'll leave it to you guys to decide. All right, so again, as we're looking at particles, just remember there's again a measurement. So again, if you got a hand lens or a microscope, it does help. And again, you can do this not just looking at sand, but even looking at buildings. If you've got brick around you or other stonework, just start looking around. See if you can tell the content, tell you what the rock is telling you. The size tells you about the erosion history. The sorting is the timing of the erosion, and how round or angular is, again, how those particles have eroded, how heavily over time. So we are going to look at some sand that is right along the California coast. We're looking at the Half Moon Bay area, right above Half Moon Bay, and baby rocks, again, decompose from that mother rock. And these different rocks then make different types of soil. That's going to be our next class. Because we're right here on the plate tectonics, you're part of that San Andreas Fault area. That's also going to dictate your rock and sand type and how quickly things can change. And we're going to compare the Half Moon Bay to Montera. So here's the Montera sand going to the beach. I'd like to go to the beach. This is north of Half Moon Bay, and it's eroding from a granite exposure. Pretty large particles. Okay, let's look at this one of Half Moon Bay. This is from sandstone along a cliff. Original rock was from the Sierras, so it's gone through several types of erosion. Let me flip back again so you can compare real quick. This is the Monterey and the Half Moon Bay. Now, this sample has a lot of magnetite in it. That's the black. So if you have a magnet with you, it's always fun to take one with you to the beach or when you're playing in the sand, because if there's any iron in there, it will be drawn to your magnet. So again, I can drag along a magnet and it'll collect all this magnetite. All right. So again, this is the Rodeo Beach sand, Marin County. It is, again, actively eroding from that surrounding rock. So when I say actively eroding, things like this, the erosion on the cliffs are breaking these rocks apart, breaking them down. You guys see the people up there? They're not far from the edge. Now see how those rocks fall down right to the bottom of the cliff, and then they get pummeled again by the waves. They continue to get pulled out to sea, washed around and pelted on. But you see the leftovers of a building structure there. Okay, so again, something had to be abandoned because of all of that erosion. All right, another place that we're looking at is the Eel River, Northern California, and it has a lot of sediment coming from it. There are different sizes of particles. You see they're definitely poorly sorted, right? It's more recent erosion, but some of them look really rounded, so that means they've been in the system for a while. And this is the eroding around an area that's an old volcanic area. So it's more of a basaltic kind of rock. All right, Capitola. Remember I showed you the mudstone with the clams in it. This is the erosion that's happening along Capitola. Look at how close those houses are. Would you be able to sleep at night? Notice the road. The road stops right there. So it used to have another layer of houses out here that then eroded and fell into the ocean. So again, our erosion is pretty constant there. All right, so here's some Monterey sand, and it's a broken up granite. So we see elements of quartz, feldspar, and hornblende, the compounds in there, angular to sub-rounded. So you kind of have to look at a lot of different pieces. And it's about a coarse grain size. Now, keep this picture in your mind. Remember that our rock cycle always continues. We never destroy rocks. They just are reformed. So our igneous rocks, again, fiery hot volcanoes, sedimentary rocks, always around water. And then our metamorphic rocks are then those that are changing, either remelting, re-cementing. All right. Now, once we've got our rocks, we don't have soil yet. We still have to add organic matter. That organic matter can be worms, it can be plants, it can be leaves, it can be compost, some kind of living matter before it becomes soil. Okay, so rocks plus organic matter equals soil. And that's what we will be doing on the next class. The next class is April 1st. So teachers, if you have not enrolled in that yet, then please do so I can get some materials and all to you. And if you need to find this little leaflet, again, it's the same place where you registered.